नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE and NEET. This is the second lecture of atomic structure, and in this lecture we are going to discuss about Schrodinger wave equation and the different graphs regarding wave function, like wave function versus radial distance, probability density versus radial distance. So let's start. The first thing I want to discuss, because I was going through the past year papers, and in 2022 they have asked a question about the graphs, different type of graphs. So let us go through the concept. Wave mechanical model. So in this, first we are going to discuss about psi versus radial distance graph. Psi is radial wave function, because we know that the complete wave function has two parts, radial part and angular part. And the complete wave function depends on three quantum numbers: principal quantum number, azimuthal quantum number, and magnetic quantum number. Spin quantum number is not related to Schrodinger wave equation. So for an orbital, three quantum numbers are required. When we are discussing about radial wave function, it is suborbit. Like if I am writing 2p, 2p is a suborbit. In order to define 2p, I need principal quantum number and azimuthal quantum number. So whenever we are talking about radial wave function, we are talking about two quantum numbers, principal quantum number and azimuthal quantum number. So this is radial wave function graph. So in this radial wave function versus radial distance graph, there are 4 points on the basis of which we can draw the graph. The first point is its value can be positive, negative, and zero. It is a wave, so you know that its value can be 0, positive, and negative. The second point is its value is maximum for s orbital at nucleus, and the logic behind is, when we are talking about s orbital, so suppose this is axis, x-axis, y-axis, and this will be the origin. So with respect to origin, when we are discussing about 1s atomic orbital, in case of 1s atomic orbital, the probability of finding electron near the nucleus will be more. So probability density is defined as the probability of finding electron near the nucleus. So in s orbital, the probability density will be more near the nucleus. As we move away from the nucleus, the probability density is going to decrease. Probability density is psi square, and psi square is related to psi. So when we are saying that at the nucleus probability density is maximum, it means that psi is also maximum, because probability density is psi square. So here, when we are discussing about s orbital, at nucleus the value of psi is maximum. When we are discussing about p orbital, if I draw p orbital, suppose I am discussing about 2px orbital. So for 2px orbital, it has dumbbell shape. So this is the shape along the x-axis. So when we are coming near to the nucleus, here there is nucleus. So as we are coming near to the nucleus, there is no probability of finding electron. So in case of p orbital, there is a planar node at the nucleus. So that's why we are saying that the value of psi is maximum at nucleus for s orbital. For s orbital, its value is maximum at the nucleus. But when we are discussing about p orbital and d orbital, you can see the shape here. This is p orbital. Near the nucleus, psi square is 0, so psi will be 0. And again, if I take any one example of d, suppose I am saying that we are discussing about 3D xy. So this is x-axis, this is y-axis, and this is the shape of 3D xy orbital, double dumbbell shape. Again, at the nucleus, you can see that this wave function is going to be 0, right? So there is no probability of, there are two nodes, planar nodes passing through the nucleus. So that's why for p and d, we are saying that the value is 0 at nucleus for p and d suborbits. And the last point is number of radial nodes. What is number of radial nodes? Radial nodes is away from the nucleus. When we are moving away from the nucleus, radial node or spherical node is a spherical shell, means it is a spherical space where the probability of finding electron is 0. So the number of radial nodes is equal to n minus L minus 1. We can also say that radial nodes are non-zero roots of radial wave function. So as we move away from the nucleus, the roots will be non-zero. So non-zero, number of non-zero roots of radial wave function is known as number of radial waves. So the number of radial nodes, so the number of radial nodes is equal to n minus L minus 1. So these are the 4 points. So keeping this point in mind, we can draw psi versus r graph. This is the graph for different type of orbital. So first, this graph is for 1s orbital. For 1s orbital, we can find the number of radial node n minus L minus 1. For 1s, the value of n is equal to 1. L value will be 0. So number of radial node will be 0. Already we have discussed that at nucleus, the value of psi square is maximum. So the value of psi will be maximum for 1s orbital. And as we move away from the nucleus, there is no radial node. And as we move away, this is going to diminish, because when we discuss about this wave function in radial part, near the nucleus, it will vary like a parabola, and away from the nucleus, it will vary like an exponential decay curve. So this is about 1s atomic orbital. There is no radial node at nucleus. It is maximum. As we are moving away from the nucleus, due to exponential decay, it is going to vanish away from the nucleus, right? Same way we can determine for 2s and 2p. In case of 2s, we are saying that at nucleus, its value will be maximum. The number of radial nodes, the value of n is equal to 2, L is equal to 0. So 2 minus 1 is equal to 1. So number of radial nodes will be 1. So here, this is the position of radial node. So here it is positive, then it is negative, right? And the amplitude at the left hand side and right hand side of this node, if you see that initially the amplitude is more, and now it is becoming small and small, right? So psi versus r graph for 2s, there is one radial node at nucleus, it is maximum, and this is the graph. It can be positive, negative, and 0. For 2p, same way we can draw that radial node will be 0. And we have seen that at nucleus, the value of psi square is 0, the value of psi is 0. So at nucleus, the value of psi is 0, there is no radial node. For 3s, same way we can draw, number of radial nodes will be 2. And at nucleus, it will be maximum. For 3p, at nucleus, it will be 0, number of radial node will be 1. In 3d, there is no radial node. N value will be 3. N minus L, L value will be 2 minus 1. So 3 minus 3 will be 0. No radial node at nucleus for 3D. This value is equal to 0. So this is psi versus r graph for different type of atomic orbital or suborbit for radial wave function versus radial distance. Let us discuss the second type of graph. The second type of graph is related to radial probability density, and radial probability density is defined as the probability of finding electron at a point in three-dimensional space. So it is always positive or 0. It cannot be negative. So the first point is its value will be positive, 0. It cannot be negative. The second point, again, we have discussed that for s orbital, its value is maximum at nucleus. Through the diagram of s orbital, we can see that as we are moving away from the nucleus, the probability density is decreasing. The third point is for p suborbit and d suborbit, it is 0 at the nucleus. And if you want to remember logically, just see the diagram, s orbital, p orbital, d orbital. For p and d, near the nucleus, it is going to vanish, right? So from there, we can remember this point. And the fourth point is the number of radial nodes is equal to n minus L minus 1. So same way, we can draw this graph for 1s atomic orbital. 1s atomic orbital, psi square will be maximum at the nucleus, and there is no radial node. Same way for 2s, the number of radial nodes will be 1, and for 3s, the number of radial nodes will be 2. It is always positive, but what is the difference in psi versus r graph? We are saying that as we are moving away, the positive amplitude and the negative amplitude in case of 2s, positive was more, negative was less. But we are taking now, we are taking the magnitude and squaring it. So it is going to diminish as we are moving away from the nucleus. The probability density is decreasing. The probability of finding electron at a point is going to decrease. So similarly, we can draw for 2p. For 2p, number of radial nodes will be 0, and at origin there is no probability density. Probability density for 2p will be 0 at origin. So this will be the graph. And same way we can discuss for 3p and 3d. So what is the difference in case of psi versus r? It can be positive and negative. In case of psi square versus r, it is always positive or 0, and its height is going to decrease as we move away along the radial distance. Its amplitude is going to decrease, right? So now let us discuss the third graph, that is known as radial distribution function. Radial distribution function is defined as 4 pi r square into psi square, or radial wave function square, or probability density, radial probability density square versus radial distance. So first, in this diagram, we have to understand that this shaded volume, this shaded diagram is representing the probability of finding electron in a volume element. So this is representing the probability of finding electron in a volume element. So we are taking a sphere from nucleus at a distance r, and the thickness of this spherical shell is equal to dr. So if we want to calculate the volume, since this thickness is very small, so 4 pi r square will be the area of this sphere, and into thickness will be volume of this spherical shell. So when we are saying that 4 pi r square dr, 4 pi r square dr into radial wave function square, this is radial probability density. If I multiply radial probability density with volume element 4 pi r square dr, it will give you the probability of finding electron in this spherical shell. But when we are going to draw the graph, we are going to draw the graph between radial wave function, which is defined as 4 pi r square, into radial wave function square, probability, radial probability density square. So here 4 pi r square into capital R square versus radial distance we are going to discuss. So again, here there are certain points. The first point is, since it is related to probability of finding electron in a volume element, its value will be positive or 0. It cannot be negative. So the first point is common as that of psi square. But this second point is important. Either it is s orbital, p orbital, or d orbital. When we are discussing about psi square versus r, for p and d it is 0 at nucleus, but for s orbital it is maximum at nucleus. But when we are discussing about radial distribution function, its value is 0 at nucleus for all suborbit, s orbit, p orbit, and suborbit and d suborbit. For all it is 0. So for s orbit, the value of psi square is maximum. The value of psi square is maximum at the nucleus. But near the nucleus, the value of this 4 pi r square term is 0, or very small value. So we can say that the multiplication of these two will be very small. So 4 pi r square is going to dominate over capital R square. So the dominating factor is 4 pi r square. So the volume element, or this surface area part, is very small. Because of that, the value of r square is maximum, but when we multiply by 4 pi r square, the net value is going to decrease, and on the basis of that we are saying that for s orbital also the value is 0 at nucleus. For p and d, the same reason, that volume element is 0 near the nucleus or at the nucleus, as well as r square is 0 at the nucleus for p and d. But for s, 4 pi r square is not 0, it is more. But 4 pi r square is very small, it is 0, but the value of capital R square is non-zero. So the multiplication of that is equal to 0. So this point is important. And the number of radial nodes is equal to n minus l minus 1. So based on these 3 points, we can draw the graph of radial distribution function versus radial distance. So here we can say that in 1s there is no radial node at nucleus. All the graph will start from 0. for radial distribution function. So this will be the graph for 1s. For 2s, there is one radial node. For 3s, there are two radial nodes. For s orbital also, all type of s orbital, it is starting from origin. For 2p, number of radial node is equal to 0 at origin. This value is equal to 0, and there are two reasons. One is volume element at the nucleus is 0, and the other value is radial density, probability density is 0. So because of that, this value is equal to 0 at nucleus. And same way for 3p, the number of radial nodes is equal to 1. It will start from origin. At origin, this value will be 0. Here you can see that the height is increasing. So there are two factors in radial distribution function. One factor is 4 pi r square and the other factor is capital R square. So on increasing the value of r, the value of 4 pi r square will increase. But on increasing the value of r, the value of r square is going to decrease. So this is increasing and the other factor is decreasing. But the multiplication of these two is going to increase. So we are saying that this 4 pi r square part is more dominating than capital R square, probability density. And that's why when we are moving away from the nucleus, the value of this graph, the amplitude of the graph or the maxima value is going to increase. So that's why we can distinguish from psi square, because in case of psi square, as we move away from the nucleus, it is diminishing. The height is becoming less and less. In radial distribution function, the height is becoming more and more, right? So that is the difference between probability density and radial distribution function. So same way we can draw for 3D, there is no radial node. So this is the graph for 3D, right? So let us move for some other point. Before moving to the other point, there is a common question regarding this. There is a point which is known as the distance of maximum probability. This distance of maximum probability, we are discussing about this point, this height. Like here only one peak is there, so this height and this height. So this distance from here to this place, this distance is known as the distance of maximum probability. So there are two questions based on this. The first one is, if you are keeping the value of L same, like if I am saying that for all S suborbit, 1s, 2s, 3s, the value of L will be 0. So as the value of N is increasing, it means that R max is increasing. It is obvious from the graph that if the value of L is same, but we are increasing the value of N, then R max is going to increase. And there is a second point here. The second point is, if the value of N is the same, but L is increasing, where we can see in third period, we are saying that 3s, 3p and 3d, there are three suborbit. So in these suborbits, for 3s, the value of N is 3, but L is 0. So this is R max. When we are discussing about 3p, for 3p, the value of L is equal to 1. N is 3. So we are increasing the value of L, keeping N same. So this position is R max. So if you compare with 3s, this R max value will be lesser than this value. And again here in case of 3D, R max value will further going to decrease. So we are saying that if the value of N is same, but the value of azimuthal quantum number is increasing, it means that R max is going to increase. So this is also important. I don't remember that in which year they have asked in JEE mains, but this point is very important. Moving to the next point, this is very common in JEE mains as well as this is very important in JEE advanced also. So be careful about these points. I have already discussed that students are confused about orbit angular momentum. Orbit angular momentum is in Bohr's theory and MVR is NH upon 2 pi. So it depends on principal quantum number, but in Schrodinger wave mechanical model, orbital angular momentum is there. So when we are discussing about orbital angular momentum is a vector quantity and it depends on two quantum numbers. When we are writing the magnitude of orbital angular momentum, we are using the formula under root L plus 1 H upon 2 pi. where the value of L for s orbital is equal to 0, for p orbital is equal to 1, and so on. So this is the magnitude. The direction of this vector quantity is given by magnetic quantum number. This question is already asked in JEE Advanced. There was a question, match the column, and they have discussed that orbital angular momentum depends on which quantum number. So most of the students have written L. That is only the magnitude. The direction is represented by ml, right? Same way, for spin angular momentum, again it's a vector quantity. For an electron, we are discussing that what is spin angular momentum. So spin angular momentum again depends on two quantum number. The first quantum number is spin quantum number, which is denoted by s. This is a spin quantum number. So its value is always positive. Its value is always half. And there is another quantum number that is known as magnetic spin quantum number, which will tell about the direction. So magnetic spin quantum number can have two values, plus half or minus half. So same way, they can ask a question that spin angular momentum of an electron depends on how many quantum numbers. So it depends on two quantum numbers, spin quantum number and magnetic spin quantum number. And the magnitude of spin angular momentum we can find out by using this formula. This is the value of spin angular momentum under root s plus 1 h upon 2 pi, where s is spin quantum number. For an electron, the value of s is always fixed, that is equal to half. So for an electron, if I am writing, if I put the value of s is equal to half, we can say that spin magnitude of spin angular momentum for an electron is equal to under root 3 by 2 h upon 2 pi. So this is about spin angular momentum. And in JEE Advanced, there was a question, and this question is very common. I think in mains also they have asked this point. The quantum number plus half and minus half for the electron spin represents the two quantum mechanical spin states which has no classical analog. Generally, what we say that when we are discussing about a spin quantum number, like if we are saying that for 3s, if there is an electron in 3s, right? This is the electron, and we want to write all the quantum numbers. We'll say that principal quantum number is equal to 3. Azimuthal quantum number will be 0 because it is in s, and there is only one orbital, so magnetic quantum number is equal to 0. When we are writing magnetic spin quantum number, then we'll write that ms is equal to plus minus half. We are writing two values, right? So this is, if you try to understand that plus half means the molecule will rotate in anti-clockwise direction and minus half means it will rotate like clockwise. This is nothing. This is just an classical way to understand. This is wrong. There is no such thing. It is quantum mechanical. So you cannot compare classical physics with quantum mechanical. So it is something related with quantum mechanical. That's why they are discussing that the quantum number plus half and minus half for the electron spin represents the quantum mechanical spin states which has no classical analog. Means it is not related with clockwise and anti-clockwise, because the word clockwise and anti-clockwise is related to mechanical or classical physics. Okay, right. So moving to the next point, magnetic moment. There are many questions of coordination compound where they are asking that for this coordination complex, what is the magnetic moment of the central atom? So we already know that magnetic moment formula is equal to under root n plus 2 Bohr's magnetone, right? EH upon 4 pi m is the value of Bohr's magnetone. So here n is number of unpaired electrons. So suppose if I am putting the value of n is equal to 1, I can write that magnetic moment is equal to under root 3 Bohr's magnetone, which is under root 3 is 1.732, which is approximately 1.8. So sometimes they will give magnetic moment and you have to calculate number of unpaired electrons. So there is a trick. If you remove that decimal part, you will get the number of unpaired electrons. Like if the magnetic moment is given 4.8, you remove this decimal point, right? This 0.8. The integer value will give you the number of unpaired electrons. So whatever value, like they have given 3.8 or 3.7, remove 0.7, you will get the number of unpaired electrons. So this is a trick to know that what is the number of unpaired electrons. Otherwise you can do calculation and find out mathematically, right? Fourth point, number of radial nodes. We have already discussed that number of radial nodes is non-zero root, right? Or it is number of radial nodes are known as a spherical nodes. So number of spherical nodes is equal to n minus l minus 1. When we are discussing about planar node, like when we are discussing for s orbital, there is no planar node, there is no plane. If I draw a plane, there is no such plane where the electrons will not exist in s orbital. So for s orbital, there is no planar node. For p orbital, if I am saying that it is 2px, then we can discuss about nodal plane. Nodal plane will be yz plane. So for s, we are saying that the value of L is equal to 0, means there is no nodal plane in s orbital. Same way for 2p orbital, L value is equal to 1. So we'll say that there is one nodal plane in p orbital. In the same way, we are discussing about d orbital, and there are two types of d orbital, axial and non-axial. So first we are discussing about these non-axial d orbitals like this. It has double dumbbell, so it may be depending upon if this is x and y, so 3d xy, or it is y and z, then 3d yz and all that. So here it is nucleus, and there are two nodal planes. We can discuss about that. The value of L is equal to 2, so number of nodal planes is equal to 2. But in this, there is an orbital 3d z square. So this is the z axis. Here the diagram is shown here, 3d z square we are discussing. So here if we discuss about nodal plane will be 0, but there is angular plane, or we can say that there is a nodal conical surface. So sometimes when we are discussing about angular node is always equal to L. That angular node will be equal to planar node, like in 3d xy, 3d x square y square, 3d yx, 3d zx. For those, angular node is equal to planar node. But here in 3d z square, there is no planar node. So this is nodal conal surface, right? One cone is there, which is passing just after this lobe along the z-axis. Along this z-axis, there are two lobes, right? So in the upper lobe, there is a cone where the probability of finding electron is 0, and there is a cone below here. So there are two cones in this. These cones are known as angular nodes. These cones are known as angular nodes, right? So it's always valid. Either the d orbital has planar node, or the d orbital has this nodal cone. So both can be represented by angular node. So that's why the number of planar nodes or angular nodes is equal to L. And if we add these two types of nodes, we are going to get the total number of nodes, and the total number of nodes is equal to n minus 1. And if they are asking that at nucleus, is it possible that there is radial node? Radial node means it is non-zero root. So radial node cannot be possible at nucleus. At nucleus, always there is a planar node. There is no radial node at nucleus, right? So I think that I have discussed about angular node. Angular node is equal to L, and angular node represents planar node, or angular node represents the nodal conal surface. So it is a common word which we can use for planar node as well as this nodal conal surface, right? So it is equal to L. Now this is a question for single. This question is related to energy, and this is a very common question, and we do mistake, though it is very simple. Whenever they are asking question about energy, first in mind we should keep that it is a single electron system or it is a multi-electron system. If it is a single electron system, then the energy only depends on principal quantum number, because you are writing in Bohr's theory that energy is equal to minus 13.6 z square upon n square electron volt per atom. For single electron system, it only depends on principal quantum number. So if I am saying that what is the degeneracy of third orbit in single electron system, third orbit degeneracy. In third orbit, all the orbitals having same energy. If the orbitals having same energy, we'll say degenerate orbitals. So in case of single electron system, all the orbitals in 3s, 3p and 3d, all the orbitals have same energy. So if we count, 3s orbital is 1, 3p is 3 and 3d is 5. So total 9, n square, 9 orbitals are degenerate in third orbit. But if the same question they are asking about a multi-electron system like H minus has 2 electrons, so it is not a single electron system, it is a multi-electron system. For multi-electron system, we are using Aufbau rule for elements like helium, lithium. Like when we are filling the electrons in these atoms, we are using this Aufbau rule, n plus l rule. So first we'll fill the electron in 1s, because n plus l value for this is 1. Then we'll put in 2s, n plus l value is 2. For 2p and 3s, n plus l value is 3. Both have equal value, but we'll fill the electron for lower value of n. So we'll fill the electron in 2p and then we'll fill the electron in 3s. So for multi-electron system, if we see, this is the lowest energy. This is the lowest energy in multi-electron system. After that, 2s is the first excited state, because when we are discussing here about H minus, this is a JEE advanced question. So when we are discussing about H minus, for H minus, if we write the electronic configuration in ground state, it is 1s2. So this is the ground state electronic configuration of H minus. So now 2s will be the first excited state. 2s will be the first excited state. Then 2p will be the second excited state, and 3s will be the third excited state. 3p will be the fourth excited state, and so on. So when we are discussing about a multi-electron system, first excited state, second, third and fourth excited state can be find out on the basis of this. And from here we are discussing that this is the third excited state, and in this there is only one orbital. So this is a question of 2015. I am reading the question, not considering the electronic spin. The degeneration, if we are not considering a spin, we are discussing about an orbital, means it depends on 3 quantum numbers. The degeneracy of the second excited state of hydrogen atom is 9, because we know that for single electron system, in an orbit, the number of orbitals is equal to n square, and all the orbitals are degenerate. While the degeneracy of second excited state of H minus, so it is a multi-electron system. So this is the electronic configuration, and from this electronic configuration we can find out that 3s is the third excited state, and in 3s only one orbital is there, so we can say that degeneracy is equal to 1. If they are asking about second excited state, we can say degeneracy is equal to 3. If they are asking first excited state, degeneracy is equal to 1. So this is a way to solve for a multi-electron system, right? So this was a question asked in 2015. I have tried my best to cover the important point in this limited time, and I am hoping that it's beneficial to you. If it is, please like and subscribe our channel. Tomorrow we are going to cover mole concept and redox, and I will try my best to give you whatever best possible within the time limitation. Thank you.